Hello students, welcome to BTech first year physics course. In the last lecture, I have introduced the concept and definition of surface integral. And I have also given few examples of surface integrals. Right? Now today, I shall discuss few problems and their solution related to surface integrals. Okay? So let's start with first problem. So in this problem, a vector field A is given like this, and S is the surface of the plane 2x plus y equal to 6 in the first octane cut off by the plane z equal to 4, which is shown over here. Now for this surface in the first octane, we have to evaluate the surface integration of the vector field A. So to evaluate that, first we have to find out the unit normal on the surface, and for that equation of the surface we have to know. Now here the equation of the surface is 2x plus y minus 6 equal to 0. Okay, and here I want to point out that wherever you get the form of the plane like this, 2x plus y equal to 6 or any other form, in that case, to write the equation of the surface, you keep all the terms related to x, y and z and also the constant in the left side of the equation and equal it to 0. Then we can get the form of phi xyz, which is actually that xyz dependent part in the left side of the equation of the surface. Okay. Then if we operate the gradient and divide by the magnitude of the gradient, we get this value of the unit normal, and a vector dot n cap will be of this form. Next, we have to evaluate ds in terms of elemental area on yz plane by the concept of taking projection of ds on yz plane, right? As you know, the direction of yz plane is along I cap, which is unit vector along x-axis. Here we have to consider the dot product of n cap with I cap. Okay, and considering this, we get this value of ds, root over 5 by 2 dy dz. Then putting this form of ds in the integration, we get this form of integral, the double integral y plus x dy dz. Now here we will do one small trick, and that is we will write x in terms of y, because you know the integration has to be performed with respect to y and z, and here the equation of plane will help us. As the equation of the plane is 2x plus y equal to 6, x will be 6 minus y by 2, right? And here the integration limit for z is from 0 to 4, because the plane 2x plus y equal to 6 is cut off by z equal to 0 plane and z equal to 4 plane, as we are in the first octane, right? And y varies from 0 to 6, right? Now, how have I calculated this? So, if you see the figure, you can see the plane 2x plus y equal to 6 cuts the y-axis at 6 unit, starting from xz plane where y equal to 0, right? Now, as you have understood how we have got this form of integration, then let's solve it. So after doing the integration and putting the limit of y and z, we get this value. Next, let's discuss this problem. So here we have to evaluate this surface integration over the entire surface S of a region bounded by a cylinder x square plus z square equal to 9 Then x equal to 0, y equal to 0, z equal to 0 and y equal to 8 planes. And here the form of the vector field A is like this. Okay. So first we have to understand how the entire surface S is formed here. So for that, let's see the different contribution of this surface. The entire surface can be formed by these 5 surfaces. Here S1 is the curved surface of the cylinder. S2 is the horizontal surface on the XY plane. Then S3 is the horizontal surface on YZ plane. Now S4 is the flat quarter circular surface on XZ plane at y equal to 0 here. And S5 is that quarter circular surface on XZ plane at y equal to 8 on this front plane. Okay. Now for all these surfaces we have to evaluate the flux. So to do that, first we will start with the S1 surface, which is the curved surface of the cylinder. Then we have to calculate the unit normal on this cylindrical surface, and that can be calculated by this formula, gradient of phi divided by magnitude of gradient of phi, right? Here the equation of the surface is x square plus z square minus 9 equal to 0, and you can consider phi as x square plus z square minus 9. Okay. Now using this form of phi in the formula of unit normal, we get this x I cap plus z k cap by 3. Then if we do a vector dot n cap, then we get 5xz by 3. Next we have to find out ds in terms of elemental area on yz plane by the concept of taking projection of ds on yz plane, right? And we get this form of ds. Now putting this in the form of integration, we get this form of integral. And here y varies from 0 to 8 because the cylinder is cut off by y equal to 8 plane on y axis, the front plane, right? Then z varies from 0 to 3 because it is the radius of the cylinder along z axis. Okay. Then if we perform the integration and put the limits, we get this value, right? Now let's calculate the flux through S2, which is the horizontal surface on XY plane. In that case, the unit normal direction is minus k cap, because when we find out flux, it is actually in the positive sense, means the outward flux we will consider. Okay, so here it is in the downward direction along minus k cap. Then the value of a dot n cap will be x, and ds is simply dx dy. Okay, then using these forms we can write this form of integration. Here y varies from 0 to 8 and x goes from 0 to 3 because it is the radius of the circle along x axis. Then after doing the integration and putting the limits, we get this value. Then for S3 surface, which is the horizontal surface on YZ plane, the unit normal n cap will be minus I cap because the flux will be along negative x direction, and that is the outward flux. Then using the form of a vector dot n cap and ds, we get this form of surface integration. After that, doing the integration and putting the limits, we get this value. Next, let's calculate the flux for S4, which is this flat quarter circular surface on xz plane at y equal to 0. Now the unit normal on xz plane in the outward direction, and that will be minus y axis. That is why n cap is minus j. Then a vector dot n cap will be of this form, and ds is dx dz. Now using these forms, we get this form of integration, right? Now here x varies from 0 to 3, and as x and z are dependent by the equation of circle, that is x square plus z square equal to 9, the variation of z will be from 0 to root over 9 minus x square on the xz plane. Okay. Now on xz plane y equals to 0, and we get this form of integration. Now to perform this integral, we can convert the Cartesian coordinates to polar coordinate, because then the integration can be easily solved. Okay. Now the relation between Cartesian coordinate and polar coordinates is like this: x equal to r cos theta and z equals to r sin theta. Then the elemental area of the quarter circular surface on xz plane can be written like this: r dr d theta, right? Then the integral takes this form. Here r varies from 0 to 3, which is the radius of the circle, and theta varies from 0 to pi by 2, right? Then if we do the integration and put the limit, we get this value of the flux through S4. Next, let's find out the flux through S5, which is the quarter circular surface on xz plane at y equal to 8, the front surface. In this case, n cap will be along positive y axis, that is j. Then a vector dot n cap and ds form will be like this. And using the similar concept of the previous case of S4, we get this form of integration with the proper limits. Now the equation of this front plane is y equal to 8. So putting this in the integration, we get this form of integral. Then after converting the integral form from Cartesian to polar coordinate, using the same concept which I discussed a short time before, we get this value. Okay. Then adding all the terms, we get total flux as 18 pi. Right. So today we have discussed two problems related to surface integrals, and I am sure that you have understood how to solve the surface integrals using the proper limits. When the surface information will be given as bounded by different planes, right? So today I shall stop here. In the next class, I shall discuss about volume integrals. Okay. So thank you for attending this lecture. See you in the next class.